Hello class, let's continue with our understanding of the concept of function, which is the sole idea in this chapter number 2. In the previous lesson, I showed you how we can interpret or we can represent a function by means of equations, the idea of mapping, right? Uh, I showed you these slides and I explained to you the ideas behind them. So, and all of these equations represent a function except this one, right? And I gave you the ideas of the tables for the inputs and the respective outputs and so on. Then I showed you the idea behind the mapping, which is basically a transformation from numbers on a given set into numbers from another set. This is the set of the independent variable, and this is the set of numbers of the dependent variable. Then I told you that we can also understand a function by means of sets of ordered pairs, like so, which basically is the same idea behind the table of values, right? Instead of writing this as a table and writing that for a for an input of -1, we get an output of 1 for this particular function. I can just write this, you see, as a point in which the first coordinate is the input and the second coordinate is the output. So we can also represent a function by means of sets of ordered pairs. And finally, as a graph. As we know, when we have equations between two variables, y and x, we can represent the y variable in the y-axis, the x variable in the x-axis, and we can plot or visualize the relationship between these two quantities, y and x, by means of a graph. And therefore, we can also visualize a function as a graph like this or like this, but not like this. Not like this, and I showed you why. I showed you the difference between these two graphs, how I can, just by looking at the graph, say that this is a function, these two are functions, but not this one. And we're gonna go over these ideas so many times. So take it easy, guys, if you don't understand very well. Okay, so let's continue, guys, with this idea. Why is a function defined as a set of ordered pairs? Let's read. In the most abstract, precise, and let's say mathematical way, a function is defined as the following. A function is simply a set, un conjunto, of ordered pairs, de pares ordenados, in which there are no two different pairs with the same first coordinate. I know this sounds extremely abstract, right? I mean, I already gave you the idea behind function. I told you that it involves the concept of dependency of a certain variable y depending on a variable x, and for one single value of x, we only get one and only one value of y. And that's very understandable for a human being, right? If you read this, like if I tell you, you know what, guys, a function is a set of ordered pairs in which there are no two different pairs with the same first coordinate. This sounds extremely abstract. You see, extremely abstract. It sounds weird. It's at first sight, it's not understandable. You see, I mean, if we compare it with the other concepts of function, right? But this definition, guys, has a very strong advantage, which I'm gonna tell you in a moment. So let's first just analyze what this definition means or what it's saying. I have here six sets. They are all sets of ordered pairs, as you can realize. Remember that these braces, these braces, they represent a set. A set. You may have a set of numbers, a set of ordered pairs, a set of letters, whatever. You can have a set of any type of object. Okay, so if you notice, all of these are sets. Sets of what? Of ordered pairs. So far we have this covered, a set of ordered pairs. Now let's analyze this important thing, in which these ordered pairs must have a characteristic that there are no two different pairs inside the set. There are no two different pairs with the same first coordinate. For example, let's look at this one. This is a set. I have this pair, this other pair, this other pair, and many more. Many more. 1, 2, 2, 3, 3, 4, etc. Why do I say that this is a function? Why do I claim that this is a function? Well, because if you pay attention to the pairs of numbers, guys, you can see that you don't have any pair that repeats the same first coordinate. Okay, I'm gonna repeat that. You don't have another pair inside here. At least you don't see it in here. And if you can catch the pattern, basically for every input, the output is just 1 plus the input. Can you see? Input, and then this is 1 plus the input. Input, and then this is one integer more, right? Input, 1 integer more, and so on. I mean, one unit more. So you can see the rest of the, you can glimpse the rest of the pairs. Okay, so I need you to understand this very well, very well. This thing here, there are no two different pairs with the same first coordinate. Oh, wait. There are, I don't have something like this, guys. In this set, I don't have something like this, 1, 3 in here. I don't have that. Okay, because if I had it, if this pair was also in this set, then this rule that is underlined would be violated. What is the rule? That I'm gonna be having two different pairs. This is different than this. You see, two different pairs, and they have the same first coordinate, 1, 2 and 1, 3. This type of thing cannot exist if this is supposed to be a function. You cannot have something like this, 1, 2, that's one pair, and another pair being 1, 3. You cannot have different pairs having the same first coordinate. Why? You need to understand why. Because we're talking about a function. For every single input x, there must be just one output. Only one, not two possible outputs. You see, if I had this pair contained in here, I would be saying that for the input 1 in x, I can have both the number 2 as output and also the number 3. You see, that's why we cannot, if a set of ordered pairs represents a function, we cannot have two different pairs with the same first coordinate. That's the rule. That's it. It's gonna take you a little time, maybe a couple of days, 3 days, to understand fully what this means. But don't worry, you will get it. You will get it. The second one, look at this. This is a set of ordered pairs, 1, 1, 2, 4, 1/2, 1/4, etc. Can you spot any pattern here? If you notice, the output is the square of the input. This is the square of this. This is the square of this. This is the square of this, and so on. Okay, so for this set of ordered pairs, we don't have two different pairs with the same first coordinate, therefore making this a function. Okay, let's look at the next one. Set of ordered pairs, 0, 2, 2, 2, 3, 2, and you perhaps may catch the pattern. What's the pattern here? The pattern is that for every number in the input, we get the same output. You see, for 0, we have this output. For 2, we have the same output. For 3, we have the same output, which is 2. And that is perfectly okay. That is completely okay. Remember that if we go to the representation of a mapping, and well, we have the input 0 and the input 2 and the input 3 and many more in there. Maybe the input uh, I don't know, 1/2, whatever. All of these are being mapped into just one output, which is the number 2. 0 goes into 2, 2 maps into 2. Pay attention to the words I'm saying. 0 goes into 2. That's why you can say it. You can say that 2 is mapped into 2. 3 is transformed into 2. 1/2 is mapped into 2. And that is perfectly okay. That is perfectly okay. All the arrows coming from this zone can land in the same number. That is perfectly okay for a function. It's not violating anything, because if you pay attention to 0, to this particular value of the input, then it lands only in one number, which is the number 2. You see, this is perfectly okay. Okay, by the way, this type of function, guys, is called the constant function. The constant function. Why? Because all the inputs go towards the same number. You see, so it's constant. The transformation is always constant. It's always the same, regardless of what number you put in here. They always go into the same number. The constant function. Let's continue. Number 4. We have this. We have a set of ordered pairs, 1, 2, 1, 3, 3, 4, etc. In here we cannot see a clear pattern, but it doesn't matter. That the fact that you can see a pattern easily or not makes no difference. Makes no difference. I'm saying that this is not a function, guys. Not a function. Why? Because these two pairs, 1, 2 and 1, 3, these are already violating my rule, which is this one. Why? Because I'm having these are different pairs having the same first coordinate, 1, 2 and 1, 3. Just like I told you here. Can you remember? So this is not a function. This set does not represent a function. What about this one? 1, 2, 2, 3, 3, 4. This is the same as this one. Well, it's also a function. And what about this one? -1, 1/2, -3, 3, -1, 1/2. You may be tempted to say that this is not a function, but that would be incorrect. It is a function. Why? Because you have these two pairs and both have the same coordinate. Can you see? But they are in fact the same pair. So I'm just basically repeating the pair. They're not different. And here we need different pairs having the same first coordinate. So even though this is a little weird, most mathematicians wouldn't do this. Like, they would not repeat the same element in a set. Like, once is enough. If you see this, that is perfectly okay, because it's in fact the same pair. You might as well discard this one and get rid of the problem. Now, in this definition, guys, which I tell you that it is the most abstract and the most precise, the most mathematical in a sense, the concept of dependency is hidden, as you can see. If I give you this definition, there is no real understanding of what a function is in human terms. There is no concept of dependency, no input, no output, no cause and effect, all the things that we've been talking about. And that's true. The concept of dependency is hidden in this definition, but it has a very big advantage. Let me tell you what that advantage is. The advantage is this, guys. Mathematicians like this extremely abstract definition for many reasons. One of which is that it is computable, computable. We can teach or program a computer how to recognize a function with this definition but not with the other ones. With what definition? The definition that I just gave you in the previous slide. A function is a set of ordered pairs in which there are no two different pairs with the same first coordinate. Okay, why? Because this type of thing, guys, the computer, which is very important for us, extremely important. This is a mathematical tool. Most people don't see it that way. They think it's just kind of like, I don't know, magic or something. But this is a mathematical tool. This thing was invented by mathematicians principally, and engineers. Okay. Imagine that I try to ask the computer which of these two equations represent a function. Okay, I cannot just ask it this question in that way. This thing doesn't understand human language, right? This thing doesn't understand the concept of dependency. It doesn't understand cause and effect. It doesn't understand the ideas behind input and output and so on. It's just a machine. It's just a machine. And this thing only understands numbers. That's all. That's all it understands, guys. Numbers, numbers. So the only thing I can do in order for this machine to recognize if which of these is a function, what I can do is this: I can program the computer to take this equation and assign some values to x. For example, assign the number 1 and get the corresponding value of y. That would be 1. And then I'm gonna program the computer to assign any other number of numbers to the input, and then calculate its output. And the computer is gonna come up with a very long list, like so. And here I'm just doing it with integers, but it can be any number. And then I'm just gonna program the computer to compare all these pairs, to compare them. Like, look at this and compare it with this, compare it with this, all of them, all the possible combinations. And then I can program the computer to recognize when one of these and one of these have the same first coordinate. And if that happens, then I'm going to program the computer to recognize that that is not a function. If these two are the same, like for example, if I had 1,1 and 1,16, okay, having two different pairs with the same first coordinate, then the computer will automatically stop and say that this is not a function. You see? And that's what it would do for this one. So this type of definition can be programmed very easily into a computer, because this thing doesn't understand any of these concepts, dependency, or the concept of for one cause, one and only one effect. This thing doesn't understand human ideas, guys. We do, but this thing doesn't. And in mathematics, it's very important that our definitions are computable. It's extremely important for reasons that perhaps you will know in the future when you go into college, into scientific careers or anything. Okay. Um, it's already 18 minutes. I'm gonna stop it right there. I've been talking too much. The rest of the class, I'm gonna take it on my own with you in these slides, okay? Because I don't want you to look at the video for too long.